Hi, welcome to the notes for 3-7. This lesson is titled, What is a Logarithm? We're going to focus on logs as inverse exponentials today. The first slide, we have a pretty long paragraph. Don't worry, I'll read it all to you. Here we go. Today's lesson will review a very important function, the logarithm, commonly called a log. You will learn how to translate between exponential equations and log equations. Exponential and logarithmic functions are closely related. Both are widely used to model situations in biology, chemistry, business, and economics, as well as engineering. Logs are useful whenever values appear over a large range. Logarithms, the word is derived from logical arithmetic, were developed in the late 16th century by Scottish mathematician John Napier, who also seems to have been the first person to use the decimal point in arithmetic as we do today. By shortening the process of computation, logarithms served for many years to speed up the work of navigators, astronomers, and engineers. Now, however, the widespread use of calculators and microcomputers has virtually eliminated the need to refer to tables of logarithms, or even to use logarithms for computations. Nevertheless, logarithms are still important in various applications, as you will see later in this chapter. Starting out, let's graph y equals 2 to the power of x and then its inverse on the axes below. I'm going to graph my y equals 2 to the power of x in blue so it stands out. This is an exponential function. Got our x's and our y's. I'm just going to make a table, throw in some input values, and then we'll pull out our output values. So when I throw in -2, I should get 1/4 as my output. -1 should give me 1/2 as my output. 0 should give me 1, 1 should give me 2, and 2 should give me 4. Obviously, our outputs are doubling each time because we're multiplying by 2 an additional time. So let's just plot those values on our graph. We've got -2, 1/4. We've got -1, 1/2. We've got 0, 1, 1, 2, 2, 4. We've graphed exponentials before, so we know it comes right along here. We have a horizontal asymptote on the x-axis. This comes in and then it curls and goes up this way. I think we'd have a point up here at 3, 8 as well. So that's what it looks like. All right, so if we wanted to graph the inverse of that, okay, we can take it and we can just flip-flop our x and y values. All right, so for this one, our inverse, we're going to have 1/4 -2, 1/2 -1, 1, 0, 2, 1, and 4, 2. And remember, if we had a horizontal asymptote for our original function, right? Let's see, that would have had like this horizontal asymptote this way. That means that we will have a vertical asymptote for the inverse. So it runs down here like that. And if we take our points and plot them, you'll see that it runs right along the asymptote as well. We have 1/4 -2. We have 1/2 -1. We have 1, 0, 2, 1, 4, 2, and I think I even threw in there 8, 3 on the other one there. I threw in the 3, 8 for the blue one. So this function runs right along that asymptote, then it curls away and curves out like this. So you can see how that would be a reflection across that line y equals x. That is our inverse function. And that is actually a graph of a logarithm too. So it says, how do we find the inverse of y equals 2 to the power of x algebraically? Well, you did learn this last year, but if you forgot, okay, we'll talk about how to do that. Remember, the first thing we did this year when reviewing our inverse equations is we took it and we flip-flopped the x and the y values. We switched them and made it x equals 2 to the power of y. right? But then we can't really solve to get y by itself the way it is. So we'll actually come back to this part here once we review that, just to make sure that we remember how to write our logarithms. Let's jump to the next slide and then we'll come back. So the definition of a logarithm. A logarithm is a way to express the inverse of an exponential function. It states here if b to the power of p equals a, then log base b of a is equal to p. So when we think about that here, right? So if our base is raised to a power, notice where our base ends up being, and we're looking at our output is a, then that means our a is going to be here, and then our statement on the left, right, we have an exponent. This exponent is our p, or power, but our log is actually equal to the exponent. So that's our way to isolate the exponent, by using logs. Okay, now an important characteristic, it says here, for when our base is greater than 0, but it can't be equal to 1. So we don't have any negative bases that we're dealing with. Okay, so below it says, example, another way to write 5 squared equals 25 is log base 5 of 25 equals 2. So just think about where everything is. We've got our base becomes our log base. Our exponent becomes our output. And then we've got, our original output here is part of our statement. So when we jump back a slide, let's finish this statement. If I have x is equal to 2 to the power of y, and I want to rewrite it to get my y by itself, we're going to say this is the same thing as log. Remember, our base is 2, which means we're going to have a log base of 2. And then we'll say of blank, right? If I treat it like it's a template, log base 2 of blank equals blank. All right, well, remember our exponent ends up being the part of it that we're isolating. So we want our log statement to equal our original point here. So which would be our y would be the output. And then we've got our value of x, which was our original output, okay, is part of our statement here. It goes right there. Okay, now there's all different ways to refer to it. Oops, I don't know why I wrote 2. Let's write x. Okay, there's all different ways to think of it there, going back and forth. A lot of people like to do the loop-de-loop thing here, or 2 to the power of y is equal to x. Oh, over here we have 2 to the power of y equals x. Okay, so there's different ways to think about it. I don't know what your teacher did last year. Hopefully you do, but we just need to make sure we're keeping it straight. The easiest part, though, is the base, right? Because it's the base here, and it's the log base there. Then you just need to think about the rest of it. All right, so next part says the base of a logarithm can be almost any value. The only restrictions are those that apply to exponential functions. Like we just stated in the last slide, b has to be greater than 0, but it can't equal 1. There are a few bases that are more widely used than others. A base of 10 is a very common base used in mathematics. Think of the metric system for measurements. Okay, so our common logarithm that we'll use, and you learned this last year as well, is that your log base 10 of x is commonly written just as log of x. So if you see no base written down here, we just go ahead and assume that this is base 10. So if no base number, then the base is 10. Now it says use a calculator to find the value of each. So down below we have log of 16. So remember, that's the same thing as saying log base 10 of 16. So, oops, that looks like 16 of 16. There you go. So log base 10 of 16. If we're just trying to find the value of that, right, we can just go in. On your TI-84s, you do have a log button there, and if you just press log, it's going to automatically treat it as base 10. So if I say log of 16, I hit enter, you see it's 1.20411, yada, yada, yada there, right? So I'm just going to round it here and say this is 1.204. Then we've got one that says log base 3 of 16. Now, depending on what model calculator you have, I know a lot of you have 84s, so there's a couple ways to type that in. Okay, notice when I pressed log, it didn't give me the option to put a base in. So you can either do alpha and then the window button, and you'll see it'll bring up a menu on your screen, and you're looking for like number 5 where it says log base. So I'm going to choose that one, and you should have something like this that pops up on your screen. You can also press the math button and scroll down, and it will give you the same option. I'm going to put log base 3 of 16, and then I'm going to hit enter. You see it's 2.5237, so I'm going to just round it to 2.524. And then we've got our last one there that says log base 4 of 16. Well, if you see here, let's do that. We're going to say alpha window, bring it up, log base, and we're going to say 4 of 16, and you'll see that will be 2. And if we take any of these and we kind of rewrite them, right, especially this last one, we'll do it first. We're thinking this is like 4 to what power equals 16? Well, 4 to the second power equals 16. The middle one, 3 to what power equals 16? Well, it'll be 3 to the 2.524, right? And it would just continue on there, would equal 16. And this first one, get rid of that. This would be like saying, you know, this is a 10. It'd be 10 to the power of 1.204 is equal to 16. So we just found what that exponent would be when it was in exponential form. So it says, write each logarithm in exponential form. All right, so we were just doing that. So remember, this is log form. Okay, this is log form that we're starting in on each of these, right? How do I know it's log form? Well, because it has the word log in it. That's pretty easy to remember. If I want to write it in its exponential form, that's where I need to go around the world, as some people call it, right? I'm going to take my base of 2, raise it to the 4th power, and it should equal 16. So 2 to the 4th power equals 16. This is the exponential form. Okay, the same thing happens here at the next one. 27 to the 1/3 power equals 3. Okay, that is again our exponential form. And then the last one, remember we have, this is like base 10, 10 to the 2nd power equals 100. All those are true statements. So exponential form and log form, they are two different things there. Whoops, that's supposed to be the highlighter. Come back. My luck. Let's just erase that. There we go. Right, so we have log form, we have exponential form. Our log form has the log in it. Our exponential form, I should have just used yellow here. This is yellow. This is our exponential form. Two different forms of the same statement. Now it says write each exponential in logarithmic form. So we have 3 to the 4th power equals 81. Let's take it here and rewrite it in log form. We're going to say log, right? Start with log. That's the easiest way, right? Our base is 3. So we're going to say log base 3 of our output. So 3 of our output of 81 should equal our 4. So log base 3 of 81 should equal our exponent, which is 4. Same thing, next one. M to the 16th power equals 12. We're going to say log. Our base is m, right? Our base is m, that's going here. So log base m of our output, 12, is going to equal our exponent, which is 16. And then the last one, we've got log base a of c is going to equal b. Hopefully you got that there. So again, You can still kind of use that around the world thing to help you get it. Let's move on. It says evaluate each. Check with the calculator. So the first one we have log base 3 of 27. We're supposed to figure out what that equals. Okay, so this one doesn't really have all of the same terms as the last one, right? When you look at these ones, right, we've got a log base, a value, and we have this output here. But with these ones, we don't have the output listed. So here's what I would do. I would say, let's just let this equal x. Okay, it's pretty easy to type log base 3 of 27 into the calculator and let it give us an answer, but what if you're asked to do it without the calculator? We are going to need to switch its form. So if we complete the statement here, it's now in log form. Right, again, we're in log form. And let's just take it here and turn it into its exponential form. Okay, so let's do that. We're going to say 3 to the power of x equals 27. 3 to the power of x equals 27. And wow, now that we've got this statement, this might be a little bit easier for us to work with. Right, think about this, 27, we could rewrite these two statements here so they have the same base. We know that 27 is the same thing as 3 to the third. So 3 to the power of x equals 3 to the third. We know that x has to equal 3. So that means that this statement right here ends up equaling 3. This value is 3. Same thing on the next one. Start with our log form. Let's set it equal to x. We'll say 7 to the power of x is equal to 1/49. Okay, so let's write that out now. 7 to the power of x equals 1/49. And 49 and 7 are compatible like that. We could rewrite these with the same base. We know that 1/49 is the same thing as 1 over 7 squared, which if I move my 7 squared to the top, I get 7 to the negative second power is equal to 7 to the power of x. And we know that x is going to equal -2. Now you can take it and type it in the calculator to check it, but I'm telling you that we're right. So x equals -2, just like x equaled 3 on the previous problem. And then let's do the last one. Let's take it from log form to exponential form. Okay, so we'll set it equal to x. Let's do the square root of 6 to the power of x equals 36. So the square root of 6 raised to the power of x equals 36. Now we can still rewrite this one as the same base as well. Right? We know that the square root of 6 could be rewritten as 6 to the 1/2 power, still being raised to the power of x. So we just took that and we just rewrote its form to 6 to the 1/2 power. We know that 36 is 6 to the second power. So we just need to apply our rules for exponents here. When we raise a power to a power, we've got 6 to the power of x over 2 is equal to 6 to the second power. Now that we have the same basis, let's just set our two exponents equal and then we'll finish solving. So x over 2 is going to equal 2. Multiply each side by 2 and we get x equals 4. And that would be the correct answer. You may take it and type it in on a calculator to double check, but I'm telling you it's correct. All right, let's move on. Got a couple more here to try. This one, log of 1. So remember, that's like saying log base 10 of 1. Let's set it equal to x. 10 to the power of x equals 1. Well, anything to what power is always equal to 1? In this case, we know that x would have to equal 0. Anytime you have that log statement or an exponential and it equals 1, we know that the power has to be 0. Then we've got log base 2 of the square root of 8. Let's set it equal to x, and then let's go around the world. So 2 to the power of x is equal to the square root of 8. Well, 8 is the same thing as 2 to the third power. And if I'm taking the square root of 2 to the third, now we can just use our rational exponent rules. We know that flower power tells us this would be 2 to the 3/2 power. Remember, power over root is equal to 2 to the power of x. And already we've solved it, right? X would have to equal 3/2 or 1.5. And now we've got log of 0.01. So again, this is one where our base is 10. We're going to say 10 to the power of x is equal to 0.01. Okay, so there's a couple ways you can approach this. If you think of 0.01, right, that is 1/100th, right? That's 1/100th. That might make it easier for you if you don't have a calculator, right? So this is like saying 1 over 10 squared, and if I want to move my 10 squared to the top, I know it's going to become 10 to the -2nd power. And now I have the same base, and I know that x is going to equal -2. And you may type it in on the calculator to check it. And I believe that is our last problem. So if you have any questions about these, please make sure you reach out. You do have to write down some of the work to make sure that you know how to do it. If you're just going through and copying down the answers, you're going to dig yourself into a hole, and this is going to get really hard really quick. So be smart about it. If you have questions, be sure to ask. Thanks for watching.